So the next thing that we should talk about is what we call line broadening. In other words, what is the actual shape of the spectral line in the spectrum? Up till now, we've really been talking about the line as if it exists exactly at one frequency, right? This central frequency that we've been calling nu naught, or maybe lambda naught for the central wavelength. But in reality, there's always going to be some little finite spread of opacity at nearby frequencies and wavelengths also. And we can use that spread as a very valuable probe of the properties of the gas or the plasma that's emitting those photons. We'll get to all that. The first reason why there has to be a non-zero spread around that central wavelength is actually Heisenberg's uncertainty principle, which you can remember from the quantum, atomic and quantum lectures of a week or two ago. If you remember, there's the delta x delta p version of Heisenberg's uncertainty principle. Then there's also the other one that happens in time, right? The fact that the uncertainty in the frequency of a wave packet multiplied by the duration delta t of that wave packet in time is bounded by Planck's constant, h bar over 2. And here, when we're talking about a spectral line that's formed by a transition between two energy levels, the light that we see, again, comes from the downward transition, the spontaneous emission of photons as it decays. And we talked about that upper state being unstable and has a finite lifetime. That is the delta t that we're talking about for the finite duration of the wave packet. That's really the same thing here. And when we go back to Heisenberg, that says that we were not able to specify that duration exactly, or specify it all the way down to 0. There's got to be if there's a finite value of that, there's also got to be a finite value of the frequency, which means for Planck's definition, E equals h nu, or h bar times omega, there's got to be a finite value for the energy too. So that means, as I say here, there's got to be this sort of quantum fuzz around the exact energy level, right? Where the energy level, E equals h nu again. If there's an uncertainty in the energy, there's going to be an uncertainty in the frequency. And when you take that and you plug it in there, that means that the uncertainty in the frequency is essentially 1 over the uncertainty, or the finite lifetime, and 1 over the finite lifetime is essentially this A21 Einstein coefficient. So that's basically giving us the width of the line. It's the minimum possible width. That's what we call natural broadening. In astronomy, usually natural broadening is too narrow to be observed. Most of the other sources of broadening that we'll talk about sort of swamp the natural broadening, but it can be measured in the laboratory. And it's well understood. Well, if there's a broadening associated with the finite lifetime A21, then it's actually true that there's also a finite width associated with collisions, right? Remember these C coefficients also have units of 1 over time, right? The C is sort of like 1 over the mean time between collisions in a system. And as I say here, the atom that we're looking at that's emitting the spectral line is sitting in a gas or a plasma of other atoms and other particles that are colliding with it, and those collisions give it a random kick of energy. And sometimes, if that happens at the same time as the photons are being absorbed or emitted, then that means that the energy levels are also perturbed by those random kicks of energy also, and we get some extra broadening too. And the frequency at which that happens has to do with how often do the collisions happen. Right? So we have to look at when is the A21 coefficient bigger than the C21, when is C21 bigger than A21, and that'll tell you which one of those two effects is the dominant one. Usually when we see this type of broadening in astronomy, it's usually the collisional effect, and that helps give us a way of measuring the density of a gas, right? The denser the gas is, the more frequent the collisions will be. So sometimes this collisional broadening lets us measure the density. Most of all the other measurable sources of broadening that we're going to talk about, though, have to do with another effect altogether. I wanted to mention these two as sort of the baseline sort of quantum mechanics ways of broadening a line. The other one is something more macroscopic. It's called the Doppler effect, and I'm sure you've heard of it. And that's what we're going to spend a lot of our time talking about here. You've seen the cartoons, you've heard ambulances go by, of course, high pitch coming towards you, low pitch moving away, and I'm sure you've seen the explanations of the fact that when something is coming towards you and emitting waves, the waves get sort of compressed, and compressed means higher frequency, less time between wavelengths that hit you, and when it's moving away, they're stretched out, and that means bigger wavelength, or bigger time, longer time between the waves hitting you, and that means a lower frequency. Right. It happens with light too, of course, and I'll bet you've seen it in other classes. The one thing that I'm not sure if you've seen in other classes is an animation that I'd like to show you that I think really nails down what the Doppler effect is all about. There it is. So now, instead of thinking about the person being stationary, let's think about the ambulance being stationary, and the person is the green thing now moving towards it or moving away from it. And what I'd like to do, if we were doing this in class, I would have you clap every time a wave hit the green thing. But now I'll just hit my pens together when we do it, and I'll wait for it to come around again. This is a really good way of doing it. So let's clap here. Do it again. Right? It's definitely, they're definitely more frequently hitting the green dot when you're approaching, and they're hitting the green dot more slowly when you're moving away. I hope that's clear to see, and I hope the YouTube animation preserves the motions well. You can always go back, and I'll bet there's other examples of this that you can find online also. I'll try to find links to them. As far as the math of it goes, we can go through a little derivation there too. Again, if you've seen it before, apologies, but I think it's good to go through it in detail just to make sure we understand where it all comes from. So we can start with a source of waves. Let's now just say light waves that are at rest with respect to the observer. If you want to know how long it takes for one full wave, exactly one node to the next, right? Exactly one, maybe not one node, but two nodes, right? One full wavelength. How long does that thing, if you're standing over here to the right, this node hits you, and then at some later time, this node hits you. What's the time it takes for that to happen? Well, if everybody's at rest with respect to each other, it's just 1 over the frequency. That's really what we mean by the frequency. So if that observer then sees the wave pass by, the actual length that is measured as this thing passes by, delta x, is just going to be that time interval times the speed of the wave, which is the speed of light. C over nu naught, of course, is just the wavelength. And again, that's what we mean by wavelength. So all these subscript 0 things are in the frame of the emitting object. But now let's put them in 2 different frames, right? If the source is moving away from the observer, we'll call that a positive velocity. That means that over the time it takes for the wave to have this full wavelength go by, from the beginning of that to the end, the object and the observer have now receded apart from one another by an extra distance, right? In addition to the c delta t, there's now this extra distance v times delta t that it's farther away by. So the length that would be measured by the observer is longer, right? So there's the c delta t, and then there's also the v delta t added on to that. And when we separate those out, we get a 1 plus v over c, and that c delta t is just the wavelength as emitted by the emitter, right? So the wavelength that's observed is longer, it's stretched out. This is now the receding ambulance version where the where the wavelengths are longer. Now, if you want to measure the time interval measured by the observer, that's also longer, right? Because that second point that I drew had to travel longer since it's further away to get to you. So that means that everything is longer by a factor of, well, it's going to be delta t times 1 plus v over c like this. And that means that the frequency, which is 1 over that time interval, is going to be lower. So this 1 over v plus c now has to go to the denominator because it's, again, frequency is 1 over a time interval. So yeah, so moving away means that the wavelengths get longer and the frequencies get lower. When v is bigger than 0, astronomers define that as moving away. That's what we call redshift for longer wavelengths. And if it's approaching, we use a negative velocity, and that gives a blue shift to shorter wavelengths. And when we're looking at lines in a spectrum, it's not just one line, it's the entire set of lines. It's the entire set of features in the spectrum that get shifted either towards the blue if it's moving towards you, or red if it's moving away from you. This equation is just another way of saying the same things. There is an exception to all this, though, and we looked at special relativity a lot in this course, and we know that when we start adding velocities to something moving at the speed of light, we have to be careful now when those velocities approach the speed of light. We have these phenomena of time dilation and length contraction, and they have to be applied here. When you do all that, we get a so-called relativistic Doppler shift formula. It still is the case that wavelengths get longer and frequencies get lower, but the details of the expressions are a little bit different. Although if you take these expressions and look at them for very low values of v much less than c, they actually do reduce to the same non-relativistic versions that I showed on the previous slide. So we do have to be careful when the v's get to be of order of the speed of light. And interestingly enough, those expressions that I just showed were also simplifications because they only apply for motions along the line of sight, parallel to the line of sight. When the motions are in some other direction, the vector v, so let's use this little n hat as something that points along the line of sight direction. If v is parallel to n, then this numerator is just going to be 1 plus v over c, and this will simplify to what I showed on the previous slide. But if v and n are pointed in two different directions, or even pointed 90 degrees to one another, right? When v and n are pointed 90 degrees to one another, v dot n is 0, but there's still an effect here. That's interesting because when our traditional thinking of the Doppler shift really only applies to motions along the line of sight. And if you were moving perpendicular to the line of sight, there really should be no Doppler shift. But relativistically, there is, and it's only gets strong when this Lorentz factor, this is the gamma Lorentz factor from time dilation and everything else, that only gets bigger than 1 when v gets to be more than 10 or 20% of the speed of light. But it's interesting that this transverse Doppler shift has now been measured in physics and astronomy, but it's a very counterintuitive thing because at very low speeds it shouldn't be there. These effects do have to be taken into account specifically in cosmology, right? In cosmology, when you're looking at very, very distant sources, everything seems to be receding from us, and no matter where we were in the universe, we would see everything else receding from us because it's essentially the entire universe is expanding. I've got some visual aids here to show how that works from Astronomy 1200. But yeah, the general idea is that we see these redshifts, and one really does have to use the relativistic Doppler shift because at cosmological distances, the apparent velocities of recession really are very large, and they do approach relativistic values. So for example, so this relative amount of wavelength stretching which is greater than 1 for velocities moving away from us. In cosmology is often written as 1 plus z, where z is what we call the redshift. So if you're looking at things in the local universe, z is roughly 0, but further away you go, z gets to be 1, 2, 3, large numbers, and the record holder is something like 11, and maybe even, in another year or so, that record might be broken again. And so it's interesting that this 11 was so long ago. 1 plus 11 is 12. That really tells us that the galaxy that emitted that light was, at some early stage in the universe, when the universe was 1/12 of the size that it is now. So it's really kind of amazing to see stuff from so long ago. The large amount of Doppler shift actually means that, the features that they saw in the spectrum were the Lyman alpha hydrogen line in the spectrum, which is usually in the ultraviolet. Here it was shifted all the way through the visible spectrum, past the visible spectrum, into the infrared. So our modern multi-wavelength way of doing astronomy is necessary for teasing out a lot of these effects. And I think that is about where this video ends. The next one, we will look more at applications of the Doppler effect to measure a lot of other properties of distant sources other than just their velocity.